Lalit, good morning, good evening. Hi, welcome everyone to the series of uh, learnings we want to promote for India, specifically Kubernetes and OpenStack. And the requirement for this stems from defining the service broker required for the CCICI for the next phase. So this is Prakash Ramchandran, and uh, I am in the board of directors, independent as a member, independent member of OpenStack. And what I propose to do is to see how we can bring Kubernetes and OpenStack interoperability for the CIP, for the CCICI. And for your information, I am also the chair of interop working group in OpenStack. So that gives me quite a bit of information necessary, which I get inputs from different cloud providers. So start with this. Here we go. First, what do we have here uh, in terms of what does OpenStack do and how do we go about it? So I'll go to the next slide. What is Kubernetes? So the definition of Kubernetes is it's a container orchestrator. Okay, so how did it come about? So Kubernetes was created by Google based on lesson learned from running container at scale for many years. So there is a background to it starting 2011, Borg and some other servers they had done, but this is an independent writing of the code from ground up, and it's a community driven, and whatever codes they develop, they donate it to CNCF, uh, a cloud native compute foundation under Linux Foundation. And now, in fact, it is bigger than the Linux Foundation itself, put it this way. But important is CNCF has the Wave. Kubernetes was its first project, and this is for container orchestration. So if you look at the diagram, you can see that you've got applications which can be run on physical servers, they can be run on virtual machines, they can be run on containers. So basically it's an application, which is cloud native application, which is being managed by orchestrator, which is Kubernetes. So traditional monolithic applications used to run directly on the physical hardware, and the OS was the key which managed everything. Then in the virtualized world, the operating system was overtaken by hypervisor, which used to manage guest operating system as part of the VM. So VM was the key. Moving forward, container is the key because the deployments occur on hardware with open operating system. And then on top of it, you have the container runtime, and containers use the container runtime, and the application reside inside container. However, in Kubernetes, there is one more element that is called pod, which consumes the container, or it is a wrapper around the container. So that's what Kubernetes is. But let's get to understand, even though all this is a known factor, but from a point of view, why do we need really either OpenStack or Kubernetes? And do they bring any value to us? Sure. Abstraction is the word where if you do not have abstraction, you cannot, everything will be splintered and there will be different ways of doing same thing, and the volumes will not be there. and then the best practices adopting is very difficult. Each one have their own. So to look at the characteristics, applications were monolithic, they moved to client server, they moved to 3-tier client server, then it has been now cloud applications came up with the web hosting and all that, and hosted that is, and now it is native, they call it. That is cloud, that's a native applications now. So container is the key and Kubernetes is the orchestrator, and all things said it's a cloud native application. Now, there are limits to everything. Of course, the footprints are different. Physical footprint is always higher, but they cannot be, you can't replicate physical servers unless you are doing virtualization, and in that case, they become the VMs. And the footprint is little smaller than the physical server. And then there are advantage of isolation, security, and all that in the VM VM footprint. And the final, we have the container footprint, which has become very popular. So a single server can have thousands of containers. Corresponding same server, physical server, could only have 10 VMs and could only have few applications. But here in the physical server, there is only one to few applications. So you can see the scales are different. Security level is different. Resource usage is underutilized in physical, better utilized in VM, optimized in same way. Scalability in physical, it's vertical and limited. In VM, with VMs, you could do horizontal and utilize better, but container provides the optimum. Same way, there are differences in whether you use bare metal with hypervisor or without hypervisor, and then you have guest OS, whether it's a lightweight process or a heavyweight. All these are all differentiable, and each of these, whether you follow the physical or virtual or containerized, each one has its own pros and cons, and the list you can go through at your leisure. So now I must come down to basics. First thing is Kubernetes is what you call a open source. It's Apache 2 licensed, and it's comes it is periodically getting updated. Of course, it's a fast moving thing because developments are pretty strong. Every quarter we are having a new versions, and that's the change is the norm here. So let's go with Kubernetes. Here what we see, integrated cloud view. And let me buzz through quickly. What is the Kubernetes principle of operation? And we will look at let's say 40,000 feet high. What are we looking at? We are looking at master nodes. Then we are looking at packaging the applications. Then you have to declaratively configure the desired state of the application while running. And of course, pods are the key here. And the deployment is a part of a, what you call, a service. And we'll describe them as we go. To start with a cluster, what is a cluster? Cluster for running application. That's what Kubernetes is. So you got cluster. What is cluster then? And cluster is a group of nodes and where the workload is being run. And all these workloads are cloud native microservices. Okay, let's look at a Kubernetes as a cluster. So when we say cluster, what you see, you got nodes. So cluster is like any other cluster. So bunch of nodes and a control plane. The control plane exposes the API. So you can see this is the control plane and it exposes the API. It has a scheduler which schedules the ask which API server passes to the scheduler. And in turn, what it does is it schedules the pods on the nodes. So you got nodes, which are worker nodes in this case. These are not control nodes, but these are workload nodes, or nodes where your applications run. Then what we have is feature sets which are offered by the controller, and that some of them are like auto scaling and zero downtime, rolling updates, replication, so on and so forth. So all those features are offered by the controller. And controller is not just one controller, there are many controllers. So it's a bunch of controllers which are offering all these services that are calling either the APIs or anybody from outside. Like example, there is a cloud controller shown here. Cloud controller is not part of the Kubernetes, is external, and it was earlier part of controller, but AWS is moved out. So all the cloud providers are now external to the Kubernetes itself, and they can also demand something from cloud to do some of the things that Kubernetes needs to provide. So we will do one thing, we will get into a few more details, how it works. So if we start, where do we start? So we start with application package. So when we have Kubernetes cluster, the master and the worker are what we call as the workload clusters. So what we do is, this is the head basically. So we can call, sometimes this is also called master and sometimes head. Or what it means is it does the decision making, it performs scheduling, it does the monitoring, it implements changes, responds to events, etc. So all of this is done by the Kubernetes master. Now, to run an application on a Kubernetes cluster, we need to do few. It follows some simple pattern. That is, write the application as a small independent microservice in your favorite language, whatever it is, and then package it, each of these microservices in its own container. Once that is done, you wrap each container in its own pod, and then deploy the pod in the cluster via higher level controller. And higher level controllers are such as deployments, daemon sets, stateful sets, cron jobs, etc. So basically you have various mechanism, descriptive mechanism available in YAML format, or that's what we call as a file. Like example, the same thing is applied even in Docker, but I will just stick to Kubernetes right now. So that's what it is. So at a high level, deployment offers scalability, rolling updates. Daemon set similarly runs the instance of a server on every node in the cluster, and stateful sets are nothing but they are stateful application components. And cron job is for the short-lived, like we do any frequently running applications like date and time, or frequently every 24-hour types of things. So the most important one is deployment. I can tell you up front because that's the one most commonly used. But there are services available besides deployments, which include stateful sets, etc., and daemon sets and all. And each one has their own role. We'll get to that later. So Kubernetes likes to manage application declaratively. That is very important, because if it has a pattern, that's the pattern. So not that it cannot do imperatively, but if you do imperatively by writing your own scripts and driving the parts, then you will not get the benefits that it offers. Not that it cannot offer imperative mechanism, but declarative mechanism is the only way you are going to get anything out of Kubernetes. Now look at the master nodes. Okay, a cluster is made of a master nodes like any other Linux host. That can be a virtual machine also, or it can be a host. So it's not that Kubernetes in itself does not use VM. You can consider, you can install a Kubernetes even in a VM. That is the master itself. Or you can do even all in one. Whole of master node can be in one node, but then that's defeats the purpose. It will not scale for you. If you want the HA capability, and if you want master to be uh, uh, able to scale as you need, and you need multi-master hosts, then you must deploy the components of the master which you see here, including the manager, the API server, HCDMN, and the kube scheduler and all on a different piece of hardware, or different piece of um, different nodes or different parts. Let's put it this way. So let's look at now API server. From interoperability point of view, Kubernetes APIs are the grand central station for Kubernetes, let's call it. Because all communication between all components must go through API. Because if you don't have API, if people don't use the API, then it is not going to be compliant to Kubernetes requirements. Therefore, all and every interaction always goes through API server. So that's key. Now, these are RESTful APIs, and what the YAML manifest, which we call sometimes manifest, the YAML document which is fed to get some work done. The work is occurring, the workload is running an application, and that application is in the worker node. And if you say that you have an application, you have to define it, and you define in manifest in a YAML file, and that also includes container image to use. So it will point to container image that needs to be used, so that that image which you have, which is a ready-made application of libraries and all that put together, that can be instantiated following whatever the configuration parameters that are described in the YAML. And it has two things, important things in terms of states. One is the scope, and that is the part scope, you can call it. You can call node scope. So every object, everything in Kubernetes is object, and the object has a scope, and you have to see that you look at what is the desired state and what is the current state. So what do the control loops which are there available to Kubernetes do? Their job is to simply ensure the state is reaching the desired state. I'll come to that. Prior to that, let's go. Once you define the configuration in a manifest, you have to store somewhere. Where does it get stored? So you have the cluster stores. The HCD which is showing here is the cluster store. So what does it have? It's a first of all, it's a single source of truth. Whatever the state of any application or any resource, it is reflected in the HCD store or the cluster store. And it is a single point of truth, and it's a distributed key value pair store. Now, the most important thing in the storages are in the in this database is, you call it key value pair, but key value is a database, let's say. What important to note is that this HCD prefers consistency over availability. So what it means is, you may find sometimes the application is not available, but you will never find that it is not consistent. Reason, if you allow inconsistency, it creates a split brain situation which is undesirable. Therefore, the Kubernetes as a principle prefers consistency over availability. Okay, that said, doesn't mean that it is not available. It will be available to the maximum extent, but preference will be based on the Raft algorithm, which is used for consensus And that's the one which is used for defining the consistency over availability. Then we have the controller manager. Now, this is where controller manager is nothing but controller of controllers. So what is controller doing? So some of the controllers do, these are all closed loop controls. What do they do? Example, endpoint controller, it manages the endpoint. Replication controller manages the replication. Then you've got deployment controller, deploys the application. And then, so all of these run in background. And in the background, you've got the watch loop. Sometimes they call it watch loop, sometimes they call it control loop, sometimes monitoring loop, or so whatever that is called, the job of that controller is to ensure current state of cluster matches the desired state. So what does it mean? It means that if a particular application is running, it has a state, it must reach the desired state. Until it reaches the desired state, the people can sleep. It is the Kubernetes controller's job to ensure that it manages through its agents like kubelet. Every node has an agent called kubelet, which reports to the API server saying, hey, what's the work for me? Give me. And once it gets the work, it goes and does the job and keeps reporting the status. But if a pod example has a container and a container as application, if the pod fails, our pod is not able to schedule, it simply reports back, hey, I can't schedule, take care. It is not its job to do anything until it is told. So the control always is in the hands of API server. So how do you logically implement control loops? So you obtain the desired state, you observe the current state, you determine the difference and reconcile the difference. And all the records are maintained in the etcd. So you have everything recorded there and you just refer to that, hey, is this the correct state? No, okay, go. What do you need to do? Change whatever you need. Tell the kubelet agent to do whatever it takes to get the job done. So control loop, watch loop, reconciliation loop all mean the same thing. Let's get to now scheduler. The scheduler watches the API server for new work, tasks, and assigns them to appropriate healthy nodes. So if a pod is failing, it will not bother about it. It will just terminate and replace it. That's it. But it in itself doesn't do it, only schedules that. It watches. So behind the scene, it implements complex logic. And that complex logic is what? So what it does is it collects all the nodes and filters the nodes which are incapable of running the task. So if there is something incapable, discard it, discard it, discard it. If there is something capable, and then rank them based on a resource being asked, what does it have? So there is a ranking algorithm like you do in search. A rank, highest rank one gets selected for a running task. But how? So what it checks is includes, is node tainted? Are there any affinity or anti-affinity rules? Is the port available on the node? Does the node have sufficient free resource? Is it capable of running anything that we need? Okay. Then is it the first in the rank? Okay, allocate it. So based on the request, it can allocate. So what scheduler does is it finds a suitable node and the tasks can be scheduled by it. Otherwise, that's it. Task will be left as pending because it doesn't have any resource anywhere. So scheduler is not responsible for running the task. It can only pick and ask the nodes to run them. Period. That's what scheduler does. Now we have got the last piece in this picture, which is cloud controller manager, which I must define before I jump to the other part. So cloud controller, what you see, is making sure that the cluster which we run can be run on any cloud platform like AWS, Azure, GCP, whatever cloud you want. So basically, out of tree cloud controllers are there which enable the application to run, same application that you can run in the on-prem can be run on the cloud in different clouds depending on the availability of the controller. So controllers must be available for cloud to which you are deploying to. So I think this gives a good picture of at least what you have here. Few things which I may not have described little detail. This kubelet. Kubelet you see here, it's a command line interface for node management on the node. Kube proxy. This is one thing which is important. Kube proxy, what it does is it enables external access to apps. So if an app is running in a cluster in a worker node, how does somebody from, no, I think that's to be corrected. Not enables external access, but rather it enables, if you have nodes, multiple nodes, within the nodes, you may have different places, different IPs. So when IP is allocated, kube proxy enables internally to be allowed for one pod to talk to another pod. And external, it doesn't do itself, but it points to the DNS or a load balancer external, which really externalizes it so that others can run through the API server from external and access it. So in itself, it is allowing the pods to talk to each other, applications to talk to each other within the cluster. Outside the cluster, it will only point to a load balancer, ingress controller, or some DNS controller, external DNS controller. There is always an add-on called internal DNS controller called cluster DNS, and that cluster DNS is a core DNS which is implemented as an add-on to the Kubernetes. So you can deal at IP level, but if you really want to deal at beyond IP level in the namespace with the DNS, then that will be the place where it will be done. So let me move you to the next slide. Sorry. So here, I think here's the next slide. So what you see here is again a different picture of the same, but a little bit more detailed on the worker node side. Because you remember that whatever we talk about, without nodes, there is nothing here. Because nodes, worker nodes are the nodes that really enable the application to be running. The control plane is the master. It manages everything, but at the end of the day, you don't want to run anything on your, unless you are a single node all in one, you don't want any worker nodes to be run on your own master, because that is, and that's leads to scaling problems. So let's assume that worker nodes are independent. Now, what do the worker nodes have? So nodes are the worker of Kubernetes cluster at a high level. They do few things. That is, watch the API server for new work assignment, execute new work assigned, and report back to control plane via the API server. So API server is the window to the worker node. And in the worker node, who does this job? Kubelet. Kubelet is the start of the show on every node. It's the main Kubernetes agent, and it runs on every node in the cluster. In fact, it's common to use the term node and kubelet interchangeably, remember. So when I say kubelet, I mean a node. So whenever you create a master, let's say that we create a control plane master, and then we have a node. So node can join the master. So when you ask node to join the master, the first thing it does it installs the kubelet on it and then registers the kubelet onto the master. So this is very important because this is how the API enables the kubelet to control the node. And kubelet, what will it do? Unless it has something to run, it cannot do anything. So what does it do? It creates a container and then runs the application container and then ensures that it wraps around and passes on. So you always need an image to run anything. So you will have it will pull the image. So example, runtime can be a Docker. Docker is a container. There are many varieties. Docker is one of them. So what kubelet does is it will create the container and a Docker container, let's say, and then pull the image and execute that within the Docker. And after it does it, it will pass on that, hey, API server, you told me to do this, it is ready. Next. But over the period, as I said, change is constant. Docker has been splintered into containerd and then is interface called CRI. And so people now use CRI or CRYO. OCI compliant, they call it. It has a specs. So what kubelet does is these days does not do directly talk to Docker, but it will go through the CRYO. Either a CRYO or any CRYO compliant or CRYO based, let's say a runtime. And runtime is nothing. It's a container runtime and it's called runc. So runc is the process. So at the end of the day, what is a container? Container is nothing but you have a piece of names, a root file system, which is a Linux file system, run within a namespace and adding to it some of the, what you call the securities like IP services or IP, whatever called IP table for the firewall rules, incoming, outgoing, incoming mostly firewall, proxies for outgoing. And then that's what you configure and that's what the runtime does. So basically the kubelet's job is to create an image which to run and pull an image using the CRYO of the either containerd or compatible runtimes. It could be Racket, it could be Rocket, or it could be some like containerd or even CRYO or even Kata for that matter. Of course, Kata is a little different game. I'll tell that later, but that's what it does. So it pulls the image, runs the image, and hands over that instance into the kubelet, into the API server, which in turn records, and so you know that an instance is running. Now, runtimes jobs is very clear: pulling the image and making sure it runs, and allocate all the resources that are required. Then we go to kubeproxy, last piece here. So Node has three important things. First one, kubelet. Second one, the container and the runtime. And the third one is the proxy. So incoming, running, and outgoing. So outgoing proxy, this runs on every node in the cluster and it is responsible for local cluster networking. So local cluster networking is called pod networking. So that pod networking is what it is responsible for. If the pod networking is, let's say, /24 or let's say 256 IPs available, so IPs one seeder is allocated, then they must connect to each other. If you have got multiple seeders or you have got /16 with 2 to the power 16 containers available in that clusters, which can be allocated, then it must be able to connect to them. That's the goal of it. And not only that, it also implements the IP tables, either IP tables, which is using the firewall, or you can use the IP virtual services, which is for the larger number. For smaller installations, you can use IP tables. For larger, you must use IP virtual services. And so the last piece, add-on piece, which I told you earlier, Kubernetes requires a DNS, and that DNS we said has to be cluster DNS, and that's the key, and that is a add-on process. So there are certain pieces like this is coredns.io, which you can what you call curl in or get the wget it or whatever, download it and run it, and that's the last piece for managing the internal, that is cluster level IP management, which includes proxy. So it talks to the proxy. Everybody can know everything inside the cluster, but nothing outside the cluster. Outside cluster is not done anything by this, but it's all managed by the controller side of it. So now that gives how to package the application as a container, wrap it as a pod, and deploy it as via the declarative manifest. That is the key portion of it. So now we have got a good picture. Here on the right side, so you can see that this is a whale or whatever we can call it, boat or whatever, but this is the Docker symbol. And same way we have kata symbol here. Kubernetes is we have seen earlier, the helm, the ship, the person who steers the ship has a wheel kind of thing, and that's the representation of Kubernetes. Now I will go to the next. Before going to the next, earlier previous past versions were all based on Docker engine. So you can have a Docker compose to compose the various containers and run them. That was the original one. But these days, even Dockers are managed through Kubernetes. And so Kubernetes is the de facto standard. And remember, there is a two words to remember: mortal and immortal. Pods are mortal. What does it mean? That means pods come and go, and they are they can be terminated anytime. Whereas VMs sustain themselves, they are not mortal. And so the kata is a VM. Kata is a VM, but run through a Kubernetes as if it were a container. So kata follows the cryo interface. So you can run kata through cryo. That's the beauty of it, even though it's a VM. So if you want some stateful application, you can use mix up with kata container. It's called kata container, but actually it's a VM, but run through cryo interface. So there is also another thing to note called KubeVirt, and that KubeVirt is important because KubeVirt is allowing a VM to be run as a container, but that KubeVirt requires that if you have container, you must be capable of nested containerization. It requires a nested level hierarchical, I mean, one calling the another, because you call as if you are calling a container, but you go and use the word library and run a VM. Therefore, the KubeVirt is that part of it. And so it is not necessary that you need another stack like OpenStack to run VM. You can run everything on the Kubernetes. Same way, OpenStack also has projects called Magnum and Zun, and those make even you can run a container within the OpenStack. So it's nothing out of way. You can choose to use either the OpenStack or Kubernetes or both or combination thereof, which is what is becoming the norm. But that's the reason that kata and container, these are runtimes. So we only spoke currently of CRI, that is runtimes for container runtime interface. Okay, open. But we have not spoken about two more interfaces. One is called the CNI for network and CSI for the storage. Those two are also important. So let's get to the next portion, and that is desired state. So declarative is important. So you declare the pods to run the applications, and the pods then use the containers, and containers use the applications. So this is one within the other within the other. And if you have VM like Kata VM, then you have one more layer which is using KubeVirt. And so these are the various ways to handle things. Now let's go to the next slide. So before I get into the interop, which is important, uh, what I see is we have only 15 minutes or so, I believe. And what I will do is I'll just run through. So you know that we have explained now what is Kubernetes, what is the principle at a high level, and what are the terms which are used. Now, getting to the APIs, there are different APIs. Of course, the grouping of APIs is somewhat different than OpenStack or any other cloud. Here, there are a bunch of uh, APIs which deal with workloads. So whatever objects that you run your container on, that is important. So you can manage and run your containers on the clusters. How? Okay, so I need to know what is a pod. So there will be a specs for pod and pod specs and pod status, and there will be a version of it. All APIs will have some group, and the Kubernetes main is called as core, which has come from Google or legacy. There is a version V1, and the kind, every uh, objects is described through some kind, and this is a container kind. So workloads are container kind, and workload API obviously have many things like workload can contain container pods, they can have deployments, they can have stateful set. So the controllers are one which control the application through the pods and containers. These have a RESTful call coming from the controller through the API, and the services they are used in deployments are stateful states or jobs. So you can have run to completion jobs. Basically, that means you start and end, and at the end of it, your container is dead because you have completed the job. So what it means is they are mortal. Pods will run to completion, period. But if you don't want to run them to completion, after completion, you still want to sustain or maintain them, you can recreate them. That is where your deployments come into picture. Because normally if a pod is run, it will run to completion, it's over, done. It is ephemeral, it will evaporate, gone. But the deployments ensure that you have how many pods, you replications, how many? You want 3 of them all the time running. This is your desired state. Okay. And then suddenly one goes away, then the 2 are remaining. Then deployment will make sure that, hey, where is the third one? It has the desired state is 3 and I only find 2. So it will go and pop up and create one more and restart, and the pod will keep running. So that's the advantage of the controllers who manage these pods and the containers. So workloads are managed through the deployments through stateful set. So if you have a volume attached to a particular container, now um, how do you attach volume to a container? You have a pod. Pod is a container. Container has an application, and container you can attach um, a you can have one container per pod, or you can have multiple container per pod. But what's the use of it? Philosophically, there are 2 ways to look at it. You can have one container per pod, and it has only one IP. Even if you have 2 containers, they will have the same IP. Pods have same IP, but they can be on different ports. So you can have a container, you can have a sidecar, we call it. Sidecar is nothing but used for sharing. So if you have applications that require, like example, if you have a web server and you have a database server, and they need to share some what do you call HTML files, they better have 2 containers and one more volume, and that volume can share. Or you can have one container, one sidecar. The sidecar can have all the files, and you can run within the same container both the web server and the database server. But that's not practical. That's not advisable. You should have two separate containers, one for the web server, one for the database, and then have some volume, which is an attachment, which is a storage volume, and that could be a piece of storage that is defined as a volume, and PV they call it permanent. It's a persistent volume that you attach. And you also may have some configuration and secrets for enabling the database, like user ID, password, and so on and so forth. So all this is part of the configuration and secrets. So this needs to be injected into the container, and that is where you can use the volumes as one of the pieces. So this is all about workloads. So let's look at the second one. And the very similar things will be there for each of them. And I will try to wrap up in 5 minutes now. So discovery and load balance. These are a group of objects that stitches your workload together into externally accessible um, applications. So if you have application you need to scale, you need a web server and database. Let's say keep the same thing. If you have web server and you have more than the single web server can handle, then you can create one more container. That means you can add one more, scale it by adding a container, and you don't need to do it. That will be done by the controller, but they will route the session through the load balancer, which is managing this web server, saying that, hey, this web server which is running on pod 1 is now not able to handle the load. Let's put on pod 2 another one. And the service called deploy will ensure that the load balancer, which is managing the application, will ask for extra pod, and that pod will be spawned by the deployer. So the control mechanism handles that. So these are something like discovery is you have node discovery. Oh, you want next, where do I put the next pod? Is this node enough? Which node shall I take? So that is discovery process. So identifying the node, the characteristics, and whatever is told by the scheduler to the kubelet, and that will find out all that and report back to the API server. So that's the way discovery will occur. And similarly, config and storage are nothing objects which are related to injecting whatever we talked about, configurations or applications, etc. They need to be. And then cluster resource objects, these are typically only required by the cluster operators, and they are usually stored in the HCD and all. Metadata is nothing, describing the data. So auto scaling and all that will have some kind of a metadata. All data will have some metadata, including the names, including the parts, including all this. So you can see that you have in the discovery and load balancer, you use services. If you have only single service, you can use services. But if you have multiple services, then you need to do ingress routing, so that you can have multiple endpoints brought to the ingress and define which service it should go to. Same way metadata, you have autoscaler, horizontal pod autoscaler means you keep increasing the number of pod or replication count, etc. And similarly, if you have some disruption, then you still need to recreate some of the things, plus event notifications, etc. These are all metadata. Same way, you got a config map, secret, and these are part I have described earlier. So basically, cluster and nodes are the important piece, and I think I am running 5 minutes to close. So you can do all the cluster registration, namespace, config map. Then you got role binding, because what is the role of the user who is an administrator or just a tenant who is using this? All these have to be defined, and the node themselves have a specs and a state. Specs is the desired specs, which is like if I want controllers, 5 pods to be running, or 5 instances to be running, whereas it is currently running 3 state, then that's the desired state is the specs. And it can be node specs, pod specs, cluster specs. You can have specs for anything. All specs means that is desired. All states means current. So there is always a gap between the current and the specs, and this is what Kubernetes keeps on playing the controller. Hey, do this, do this, do this, so that they maintain the state. So even for rolling upgrades, version updates, we don't have to worry. It is, if you choose the right deployment, it will address that. So each of these daemon set, deployment, cron job, and all that job, etc., I have got as typical characteristics, and we must know what deployment service, which service to use, and that will take care of this. So last and but not the least, this is to, I am closing today with Cluster API. Cluster API is a sub-project of Kubernetes. Kubernetes simply handles one cluster, no more than one. If you want to do multiple cluster, then you have to go to Cluster API. And Cluster API is the one which handles upgrading for provisioning, upgrading, everything for multiple Kubernetes clusters. I think with that, Cluster API here, you can see with Cluster API, you can manage the machines, whether it's a bare metal machine or you have some infrastructure provider, which is different from them, like cloud service provider. And that can be either a on-prem, could be VMware on-prem, OpenStack on-prem, or it could be some other provider where you will manage. So Cluster API at the concept level is for managing, and you can see this is the Kubernetes symbol, which is important. So anybody who is managing through Kubernetes will put this. So I think with that, I will just end up with OpenStack has very similar concept, but it does at a different level. It does at the VM. So what is applicable to VM is applicable to what is applicable to containers and pods. In pod is the unit of scheduling in Kubernetes. You don't even talk containers. You only talk pod. Pod contains containers. That is clear. Same way, the unique entity for OpenStack is a VM. You only talk in terms of VM. So anything that deals with APIs, whether it is a compute, storage, networking, container, even containers, of course, it has its own containers. That's the one which is different. But otherwise, storage, shared file system, most of these services are tied to VMs. And the last piece, Keystone Identity Service is the key. And like in the case of Kubernetes, the role-based access controller, RBAC is important. Same way, Keystone is important. I think with that, I will end the call today, or at least I'll stop recording, and before I open the floor for a few minutes before I close. Thank you very much, and I will stop.